So in the last few videos, we've mentioned that there are 4 properties or variables with gases that we can look at in these little gas laws. We've looked extensively at the relationship between pressure and volume and temperature, but we've always ignored moles. The moles have always been constant until now. Avogadros Law. Avogadro, this is the same Avogadro that came up with the whole mole concept, the 6.02 times 10 to the 23rd particles in 1 mole of any gas. And now he's going to expand on that a little bit and say, if you have equal volumes of gases, and they have to be at the same temperature and pressure, they will have the same number of particles. So this little Avogadros Law is looking at the relationship between volume and number of particles, and the number of particles is usually measured in moles. So yes, it's the same Avogadro. And just like what we had said before, if you want to look at the relationship between number of particles and volume, then you need to keep the other variables constant. In this case, that would mean temperature and pressure. Okay, so here's what happens. Let's say I have these 4 balloons, and they're filled with different gases. If they're at the same temperature, the particles have the same amount of kinetic energy, which means they're going to have equal amounts of collisions. And if they're at the same pressure, again, there must be the same amount of collisions inside those balloons. So if there's the same amount of collisions, expanding them to the same volume, there must be the same amount of particles inside the balloon. Now I think here's what confuses people about Avogadro's Law. Let's just randomly add in some molar masses. So this would be N2 diatomic nitrogen. Let's call it approximately 28 grams per mole. Let's call hydrogen about 2. We'll just kind of estimate these. Argon. Oh, let's just go like 40 grams per mole. And CH4, let's say 16. I think people have a hard time understanding why these balloons would have the same volume when they have different gases, and their gases have very different masses. Well, here's one thing that we should make note of. Because they have different gases, they will have different masses. And I could even go a little bit further and say densities. They're right. So if you were thinking that the first time you were kind of looking at these balloons, yes, you are right. These balloons will have different masses and different densities. They're different masses per the same volume. So that's why their densities will change. And so yeah, I mean, if I have these balloons, the argon balloon is going to kind of sink in air, whereas the other ones will kind of float in air. So you are right. They have different masses. But we're saying that they would expand to the same volume. Because they're the same volume, there must be the same amount of particles in each balloon. There's the same amount of collisions, expanding those balloons to the same volume. Same amount of collisions, they're at the same temperature, so the particles all have the same amount of kinetic energy. And if there's the same amount of pressure inside the balloon, again, that kind of means that they must have expanded to the same volume. If you have equal volumes at the same temperature and pressure, they must contain the same amount of particles. But they will not have the same mass. So that's what they might do, like, let's say this was a multiple choice question, and they have, balloon A, B, C, D. And they might say, like, which one will have the greatest mass? Well, trick question. You look at the molar masses on the periodic table. Yes, they have different masses. But then if they said, all of these balloons have expanded to a volume of 1 liter or whatever, at the same temperature and pressure, If they're equal volumes at the same temperature and pressure, they have the same number of particles. And so then that's kind of the trick question that people will think, well, the one with the biggest mass, the 40-gram molar mass of argon, maybe that's going to be the biggest balloon. Well, I mean, it's going to be the heaviest balloon, but it's got the same amount of particles, the same amount of collisions. It'll expand to the same volume. If they're equal volumes, they must contain equal amounts of particles. Now here's how you might apply this. Ooh, this looks like maybe a little stoichiometry. I have an equation. We've got some oxygen gas, and we're going to turn it into ozone, O3. We have a 12.2 liter sample containing about half a mole of oxygen at 1 atmosphere and 25 degrees Celsius. We'll assume that those conditions remain constant. All the oxygen is converted to ozone. Oh, there it is, at the same temperature and pressure. What will be the new volume of the ozone? So we do have to do a little stoichiometry. Can't wait. Okay, so first we need to figure out, if I have 0.5 moles of oxygen, how many moles of ozone should be formed? And from there, I should be able to convert that to volume. All right, so we'll do the stoichiometry. We have 0.5 moles of O2 oxygen. I'm going to cancel what I have, the O2. We're going to switch it to what we want, O3. It's a 2 to 3 ratio, which leaves me, if we go like 2 sig figs, we'll say 0.33 moles of O3 ozone. Fabulous. Okay, so now, if this is a directly proportional relationship, if I have a larger volume of gas at the same temperature and pressure, it should contain more particles. More volume, more particles. More particles, more volume. Then again, we should be able to set these two conditions equal to one another. So let's see what we had here. And again, it doesn't matter the identity of the gas. It doesn't matter that we're talking O2 versus O3. All we care about is number of particles. So according to this balanced equation, I'm going to end up with less particles. That should create a smaller volume. It doesn't matter the identity of the particle. Like those balloons. The volume is the same regardless of the identity of the particle. The mass would be different. Okay, so let's do a little relationship here. Let's set up a proportion. The original volume was 12.2 liters, and that was per 0.5 moles. All other conditions are the same. Temperature and pressure are the same. I just have less particles now. I want to solve for the new volume with only 0.33 moles. So we plug this in our calculator. And with sig figs, I would usually go back to the original volume. So if the original volume had 3 sig figs, I'm going to leave 3 in my final. I get it that like the moles have 2. And in general, if this were free response, you have a buffer of like plus or minus 1 in the sig figs. But I usually try to be consistent with all the same kind of data. So I'm going to say my new volume is about 8.05 liters of O3 ozone. Didn't matter the identity of the particle, just the amount. I have less particles. So less particles should have less collisions. That should create a smaller volume. And this makes sense. Volume went down by a little bit. As long as temperature and pressure obviously are held constant.